Good morning. I am Dr. PKS Nen from School of Mechanical Engineering. Today I am going to teach the course Mechanics of Material BTME 2008, and the topic for today's discussion is strengths and deformations. Recapitulations. What we have done in our last lecture. In our last lecture, we have discussed what are direct loads, and we also classified them into tensile and compressive point loads. We also discussed uniformly distributed load and constantly varying loads. Then we discussed internal resistance generation mechanism of material, and we discussed that whenever there is a load applied on the body, it tries to change its shape when the force is applied. Either if a point load is applied on the bar along a longitudinal axis, it will tend to compress it or increase it depending upon whether you are pulling the bar or if you are pressing the bar. So say if you are pulling the bar, what will happen? The interatomic chains, they will try to resist the deformation because of the coherent forces, and they will collectively try to oppose any change in the shape, and that creates an internal resistance to deformation. And that is how, in response to externally applied load, the internal resistance is established, generated inside the material. We also discussed that for equilibrium purposes, this internal resistance should be equal to the externally applied force, because summation of forces whether in horizontal direction or in vertical direction should be equal to 0 for equilibrium. Hence, the externally applied force should be equal to the internal resistance offered by the material. Based on that, we defined a quantity called stress, and that stress was calculated as the force per unit area with units Newton per meter square or pascals in SI system of units, depending upon whether the load and the stress is trying to increase the length of the bar or it is trying to decrease the length of the bar. The stresses were classified as tensile stress and compressive stress. In the in the case of direct stresses, the loading is uniaxial, means the forces are equal and opposite, and their line of action is also same, and it is applied at the extreme ends of the material, opposite extreme ends of the material. However, consider a situation in which the load is applied on the opposite forces, but the line of action is different. They are parallel, but they are separated by certain distance, say d. What will happen to the material? So one force, say on the left, will try to slide the upper layer of material towards it, and the other force towards the right will try to pull the body material to the right hand side. So what will happen? Their line of action is not same, and they will like to shear apart, or the layer of material will glide over each other or slide over each other, and this phenomena is known as shearing. So this will generate internal resistance by the material, in which the stresses which are generated are known as shear stress, because they are basically resisting shearing of the material, and the stresses are tangential to the surface. In the case of direct load, they were normal to the surface, but now here the vectors, force vectors are lie within the plane. We also demonstrated towards the last portion of the lecture that it is not possible for a shear stress to exist alone, because we are having a two parallel forces, the line of action of which is different and the forces are unlike. Hence, they are forming a couple or movement among themselves. When they are finding a movement, creating a movement for equilibrium of the body, it is necessary that the movement should be balanced, and we discussed there that in order to balance the movement at the plane set 90° to the originally applied forces, there will be automatic generation of the stresses which are known as complementary shear stresses, and we studied the property that the complementary shear stress magnitude is same as the originally applied shear stresses. Now we come to the today's lecture objectives. Today we will discuss St. Vincent Principle. We will study strain and shear strain. When now we become conversant with the stress as well as strain, we try to study what is the relation between them, and the Hooks was the first person to come up with a law according about the relation between stress and strain. Then we will study that, and based on the Hooke's law we will try to define two material properties which are known as modulus of elasticity and modulus of rigidity. Based on the entire knowledge gathered so far in the lectures, we will try to establish an expression for calculation of deformation in the bar under single loading. But what happens if the bar is subjected to multiple loads at different section or at the same section? Then we will have to use a special principle known as the principle of superposition in order to study and calculate the deformation in the bar. We come to now St. Vincent's principle, and in St. Vincent principle, if you see the figure on your right hand side labeled as figure A, which is the top figure, here you will see 2-point loads P are applied in line, means they are uniaxial, line of action is same, they are uniaxial, equal and opposite compressive loads, point loads applied with magnitude P on the cylindrical bar. For our demonstration purposes, the entire cylindrical bar has been marked like the grid. Grid lines has been marked on the surface of the cylindrical object, so that one is along the longitudinal axis and other axis is parallel to the transverse axis or perpendicular axis to the loading. If you see what happens when the load P was 0 and then it was applied with magnitude say 5 kilonewton, you will find that all the lines, vertical lines, remain parallel to each other even after the application of load. Though if you look at them carefully or you measure the interline spacing, you will find the distance between perpendicular lines is shrinking, because it is a compressive load trying to decrease the dimension of the material. So the grid lines, perpendicular grid lines, will become closer, but they will remain parallel to each other. So this is the ideal situation in which you can say the stress distribution is uniform across the whole cross section of the beam. The magnitude of the stress is same even at the extremities or at the center. The magnitude at 3 points will remain same. But come to the second case, which is shown in figure B below, you will find that the compressive load is applied, but the end rigid collars are missing. So what is happening? The compressive load P is directly applied at a single point on the material surface. What happens? Due to the stress applied at a very small load applied at a very small area, the stress intensity at the local point of application is much higher as compared to the two extremities, and hence it tries to push this point inside, and the grid line deformation becomes as it is shown in the figure. But if you look at the what pattern is being observed in this figure, that up to 3 grid lines from the either corner, you will find the lines are not perpendicular. The perpendicular grid lines become inclined to the longitudinal axis. But however, in the shaded zone which I am showing right now, you will find the grid lines are still parallel to each other. The transverse grid lines or perpendicular grid lines are still parallel to each other. This means pattern shows that for the initial certain length of the material longitudinal bar, the stress distribution was not uniform, but as soon as these lines become perpendicular lines become parallel to each other, the stress distribution becomes uniform, and hence the general formula for calculation of stress, that stress is equal to force per unit area, holds good only in the colored or shaded blue region, gray region of the figure. While in the upper figure, the same calculation formula was applicable throughout the length. But in this case, when the rigid collars are absent, certain region at the two extremities is to be excluded. So Saint Venant was the first person to study this distribution, and he gave a principle for that, named after him as Saint Venant's principle. According to this principle, the distribution of internal stresses or strains, it is applicable, please note that it is applicable for both stresses as well as strains on the section of the body, which are at sufficient distance from the surface of load application, means say within the gray zone in the lower figure, is not affected by the nature of actual application of load over the surface. Means if you consider in the case A and case B, what is the difference? In case A, the material feels the point load as a uniform distributed load because of the presence of the collar, rigid collars. But in the second case, the low point of application is directly applied on the material. Hence, the nature is affecting certain corner region of the cylindrical bar, but not the middle portion of the bar, and that is what it is said in the Saint Venant principle, that the stress or strains on the section of body which are at sufficient distance from the surface of load application, means extreme corners, is not affected by nature of actual application of load over the surface. It is not affected whether you are applying a point load as lowercase or you are applying as a UDL as the upper figure. But then comes the question, how much is the reason we need to exclude for distribution, stress distribution to become uniform? So Saint Venant formally studied this systematically and found out that if the d is the diameter of the cylindrical bar within a distance of 2d to 3d distance from the corners point of load application, the stress distribution becomes uniform. So if you are calculating stress in the gray region, the gray region or the unshaded region is maximum up to 3 times diameter of the bar on either corner. So that is known as Saint Venant's principle, and the calculation of stress as the load per unit area holds good only in the region, central region, which is away from the point of application of loads. Now I am going to show you a concept video taken from the YouTube. This is about the strain, which is a quantity that describes the deformation that occur within a body. Consider a cylindrical bar of length L under a green load shown by a. Here it extends by an amount delta L. So delta L is the change in length, while L is the original length of the body. So the strain epsilon is known as delta L by L. This is called normal strain because it acts in the normal direction, and it is produced by normal direct stress. It is generally represented in terms of the percentage. If we consider the stress strain diagram, these two are related, and to find the relation we will have to take help of the universal tension machine. So a specimen is kept there, and if load is gradually applied, stress and strain diagram is plotted. The initial portion of the stress strain diagram is linear. This is the elastic region in which any deformation on the removal of the external load is completely recovered. Here the Hooke's law is applicable, which states that stress is directly proportional to strain, and that can be represented as a single law, sigma equal to E times epsilon, where capital E is the Young's modulus or the constant of proportionality. The other portion of this diagram is the plastic region, where deformation is not recoverable. So now we are ready to talk about strains. So as we have seen, the deformation of body under a load is proportional to its length in the linear region. So see the figure which is shown below. If the force F is pulling a original body of length L and causing a deformation delta L, the strain will be change in length by original length, that is delta L by L. This is known as longitudinal strain, epsilon equal to delta L by L. As the dimensions of change in length to the original length are same, it is a dimensionless quantity. In the case as tensile stress is considered positive because it is increasing the length, the tensile strain is also considered as positive, while the compressive stress on the other hand is considered as negative, hence the corresponding compressive strain is also taken as negative. Next we come to the shear strain. The shear strain, it is defined as the change in right angle of the element measured in radians. It is also a dimensionless quantity. Let me explain the shear strain in slight detail to you. Consider a rectangular block, which was originally a rectangle. But when you applied the shear stress on the top and bottom plane, and the bottom plane is rigidly hold its place, what will happen? The top surface will tend to slide to the right hand side, and this will deform the perpendicular 90-degree angle of the rectangle by 5 degree as shown in figure. This phi measured in radians shows the shear strain. It is basically representing distortion of the rectangular element shape. The more is the distortion, the more is the shear strain, more is the phi. So, can we calculate it? How to calculate it? Actually, you know, the phi it can be measured as the arc upon radius. If you take this distance AB to be very small and the deformation phi to be very small, the AA arc can be expressed as the straight line deformation AA dash. That is, if you look at this triangle A dash, A and B, tan phi is equal to A dash A divided by AB. And hence, when the phi is very small, you can safely assume tan phi is equal to sin phi, and sin phi can further be assumed to be phi. And hence, this basically phi can be represented by tan phi for very small deformation. So this is a discussion about the strain, shear strain. Shear strain is a dimensionless quantity and it is measured in radians. Now we come to Hooke's law and modulus of elasticity. The Hooke's law, as we have seen in the video, states that within elastic limit, strain is proportional to stress producing it. So that is what I am writing here. In the second line, stress is directly proportional to strain because it was a linear region in which the Hooke's law was applicable. It is the linear region represents the elastic region where the deformations are completely recoverable. Means any specimen on any material deformed within the elastic limit will regain its original shape once the external load is completely removed. If you introduce the constant of proportionality in this sigma is proportional to epsilon, you can define the constant of proportionality as E, that is Young's modulus. Young's modulus becomes equal to sigma over epsilon. So this is known as Hooke's law, and E is known as Young's modulus of elasticity. For elastic bodies, the ratio of stress to strain is known as Young's modulus or modulus of elasticity, and it is a property of the material. So if you look carefully, the stress required to produce a unit strain is called modulus of elasticity. Since the quantity in denominator, that is epsilon, has no unit because strain is a dimensionless quantity, the unit of Young's modulus E is same that of sigma stress, and hence the Young's modulus will have the same units as that of stress, and it will be expressed as Newton per meter square. Some few points more about modulus of elasticity. Young's modulus is the stress required to cause a unit strain, as we have discussed in the old slide. What does it mean? Unit strain means delta L should become equal to L. Only then the strain will become unity. So the unit strain means elongation of body equal to its original length. That delta L should be equal to L. And this implies that the Young's modulus is the stress or force required to per unit area to elongate the body by its original size, or its length should be doubled. So that you see, for most of the engineering materials, the strain generally is 1 in 1000. Means if you having 1000 millimeters, only 1 millimeter strain is observable. Maximum, that is the maximum deformation observable generally. So that means for engineering materials like steel, the strain is a very small quantity, and the force stress divided by a strain, and strain is a very small quantity of the order of 1 in 1000, the Young's modulus is very high for steel. But on the other hand, you see, if you take a rubber, then for a rubber, if you increase its length to its double, means with very small force or very small stress, you can get very large value of stress. So small value of stress divided by the large value of strain, the Young's modulus of elasticity for rubber is quite less than steel. However, this looks quite contradictory, because generally we feel if anything which is extended easily is more elastic. That is not true. Elasticity, or Young's modulus of elasticity, is more for steel than for rubber. Though the steel deforms under very high load by a very small quantity, and the rubber deforms under very small load by very large quantity, and that explains that the steel is more elastic than the rubber. So never get confused and don't feel this misnomer that the rubber is more elastic than steel. Next we come to modulus of rigidity. In modulus of rigidity, within the elastic limit, the shear strain is proportional to the shear stress producing it. The same it is if you look at this rule is exactly parallel to the Hooke's law. So Hooke's law is same for the direct stress as well as the shear stress. Means shear strain is proportional, phi is proportional to tau. And if you include the constant of proportionality, tau can be expressed as equal to g times phi. This constant of proportionality g, which becomes a ratio of tau upon phi, that is the ratio of shear stress to shear strain, is called modulus of rigidity. And for elastic bodies, the ratio of shear stress to shear strain is constant and is known as modulus of rigidity, and it is also a property of the body material. And you now remember the modulus of elasticity, that is Young's modulus, and modulus of rigidity, both are properties of material. Now we will try to calculate the elongation of bar. Consider a bar of area, cross-sectional area A and length L, subjected to a force P as shown. If the deformation is delta L, the strain would be delta L by L, and the stress would be equal to load force P divided by unit area as shown here. Hence, since epsilon is equal to sigma upon E, delta L by L becomes equal to P upon AE, or delta L become equal to PL upon AE. Means the deformation or elongation of bar delta L can be calculated as in the new ratio in the numerator, the load multiplied by its length of original length of the bar divided by the product of the area of the cross section and Young's modulus of elasticity. So delta L equal to PL upon AE is the formula for calculating elongation of a bar. Now we come to towards the principle of superposition. What will happen if a bar is subjected to multiple loads, or different sections of a bar are basically subjected to different loads? So what will happen then? It is quite obvious that we will sum up the individual deformation of different sections, and together that will contribute the total deformation of all the bar having various sections. So you sum up the deformation of individual sections. Say there are 3 sections, so you sum the deformation of section 1, then section 2 and section 3, add them together, and that will give you the total deformation of the bar. Or if there are 2 loads, you can in a same section of bar, you can calculate the net load on the bar and can calculate the total deformation of the bar. This is, in simple terms, is known as principle of superposition. The principle of superposition basically states that if a body is acted by number of loads on various segments of the body, then net effect on the body is sum of the effects caused by each of the loads acting independently on respective segment of the body. Thus, each segment should be considered individually into an equilibrium, and this is done by making a diagram of segments along with various forces acting on it. And if you remember the engineering mechanics background, this diagram is referred as the free body diagram. You remember in the engineering mechanics diagram, a mechanics course, we said the free body diagram are the diagrams in which a body is freed from the contacts, all the contacts, and only the forces acting on it, weight of the body, and the reactions are considered in the body. So the principle is surprisingly, the principle is of superposition is applicable to all parameters, whether it is calculation of stress or calculation of strain or calculation of deflection. So it is not only the deflection which follows the principle of superposition. You can calculate the stress also in the similar fashion, and in the similar fashion you can calculate the strain. However, it is not applicable for the cases where the Hooke's law is not followed, because in the non-linear stress strain characteristic or plastic deformation, the Hooke's law is not obeyed, and the deformation formula which we have calculated previously is based upon the Hooke's law only. So now to tackle as a homework today, we are giving you a numerical in which a bar is subjected to different forces in different segments. So you have to use principle of superposition in order to calculate the total deformation of the bar. So you see there are three segments, AB, BC and CD. You make three free body diagrams, calculate the deformation in individual segments and sum them as total delta or delta equal to delta AB plus delta BC plus delta CD in the individual sections. Here are the references once again. We have the textbook followed by S.S. Ratan, Strength of Materials book. From Tata McGraw-Hill Education, we have used reference books as S.P. Timoshenko and R.K. Bansal, Strength of Material. So that's all for today's lecture. Thank you and happy learning.